Okay, hello, this is Dr. James, and today we're going to do some cool science today. I did a video recently on exploding water, showing how water explodes when you put high voltage onto it. And I just wanted to do some studying of this phenomenon, and I had a theory here. We're going to try to measure the dielectric strength of water. So basically, what these are, these couple plates up here. Tape's picking up some stuff. So we have a couple plates here. Okay, so we have a couple plates here, and two copper plates, and I put some tape in between them. And so what the idea is that capacitors can hold a certain amount of energy, and that energy is related to the dielectric constant, which is basically how much it distorts the electric field, how much the atoms are like a spring, and when you put electric field on it, it like compresses them and it absorbs some of the electric field. So some of the energy is stored in these atoms as they're compressed or basically stretched by the electric field. It tries to pull them apart. And you can keep on storing energy in a spring until the spring breaks, until you push it too far. And the same way is true with the atoms. The atoms have a dielectric strength as well, which is the point at which they break. So basically the equation for energy density in a capacitor is 1/2 CV squared, or epsilon CV squared. So the epsilon is the dielectric constant, and the dielectric strength determines the maximum voltage you can put on there before it breaks down. So I had a theory that possibly we're getting an arc. Basically, we're exceeding the dielectric strength of the water, and so if you're below it, it's a very sharp transition. Below it, it kind of fizzles and it bleeds off the electricity because water is a little bit conductive. But above that, I believe it basically forms an arc and basically catastrophically breaks down the dielectric material and produces a very fast arc which blows things apart. And so we were going to look at that. And here, let me see. The dielectric strength of water is about, the given value is between 65 and 70 megavolts per meter. Okay. And what that means is this electric field is independent of the voltage or other things. It's independent of geometry. It's something that the atoms would see directly. It's just the field at the atoms, and so it's like a material constant. Or you can apply it to the material constants to see what voltage they break down at. And so this is the given voltage. So what I intend to do is just need to make a very small gap because I'm not going up to very high voltage. So I have some tape on there, and I have this capacitor plate, and then I'm going to take the other plate and put it on top and have it separated by a very thin spacing, and put water in the middle between these two pieces of tape here. So those two pieces of tape will hold the plates apart at a very short distance. And then I'll slowly bring up the voltage until we get breakdown, and then I can measure at what point the water breaks down. And so I get a measurement of the dielectric strength of the water and see if it compares to what we're looking at here with the 65 to 70 megavolts per meter. Should be interesting. Okay, let's get going. Okay, so here we have our tape, and here is our calipers. And let's just measure how thick this tape is. And it is about, can we see that? 0.06 millimeters thick. Okay, that's how thick the tape is. Okay, so I'm going to use that as a spacing for my capacitor, my water capacitor. Okay, so I polished up a couple pieces of copper, and that's probably like, what, an 1/8 inch thick. Okay, and I'm going to put some tape on one of these as a spacer. Got the tape there, let me cut that out. Okay, so I'm going to try to measure the critical electric field, since I know the thickness here, for this effect to happen. And I'm just using tap water right now, although I probably should be using something more like reverse osmosis or something. We'll see how the tap water works. Okay, I'll put a little bit of tap water on this guy, and try to keep these plates clean. Okay, we have a very thin gap across there, and I'm going to set this on top of our aluminum electrode, and then I will touch. Let me get this on. I'm going to have to use two hands to get that, I think. Maybe. Okay, there we go. I'm going to use a aluminum electrode on the other side as well to make the contact. Oh, come on. And let me, this thing, I'm going to put some here so it doesn't freaking cause a disaster. I'm going to start this out at 10 volts and work my way up in 10 volt increments. Okay. Looks like 44 is about the lowest voltage that I can start it at. Let me remove it from the charging supply, and we will give this a test and see how this works. Okay. Not too much. That's interesting. The voltage dropped to -13. Okay, we'll try to go up to a little bit higher voltage. See what happens. Okay, so I have that set to about 50 volts, and I'll disconnect the charge to it. And let's give this one a try. Okay, did I get that? 50 volts. Okay, so I guess it dropped to 23, and I guess everything's negative, 23.5. Okay, so I set this level to about 60 volts, and we'll give this one a try. There we are at 60. And, oh, let me disconnect the charge so I know how much it leaks down to. Okay. I kind of moved that time. Looks like it went down to about 44 volts, 45 volts. Okay. Okay, I had it at 70. Let me just pump it back up to 70. Maybe it's not going to go back up. There we go, 70. Okay, disconnect the charging over here. And we'll see what 70 does for us. Still kind of a fizzle. Down to about 39 volts. Okay. Okay, so we're basically at 80 volts right now. And we'll give this a try. I've disconnected the power over there. 80 volts. Wow, the spark's getting more aggressive. Drop down to 43. Okay. Okay, so we're basically at 90 volts now. We'll give this a shot. I have the power disconnected. Okay. Down to 44. Okay. Okay, so we're basically at 100 volts now, and we'll see how this behaves. Okay. Down to 58 volts. Okay. Okay, so we're skipping up to 120 now. We'll see how this behaves. Okay, and we're down to 60, and I have been replacing the water now every time, and it looks like it's starting to, there's some marks in there, starting to discolor down there. Put some more water on. Again, the electrode that is starting to discolor is the bottom one, which looks like it is hooked up to, well, this side right here, which I think is probably the negative side. Is that right? Well, that's the positive side. It's hooked to the positive side. Okay. So this electrode that's discoloring, starting to rust, or oxidize, is hooked up to the positive side of the capacitor. Okay, so now we're at a charge of 140, and let's see how this guy goes. Okay, and it's down to 70. Okay, so it looks like we are at 160 now, and let's just give this a shot. Down to 89. Okay, so we're at 180 basically. Now let's give this a try. Okay, down to 85. Okay, we're at 200 volts right now. I'll give this a shot. Down to 118. Okay, so we're at 220 now. Let's give this a try. Okay, we're down to 65. Okay, so we're up to 240 now. Let's give this a shot. See what happens. Oh, wow. That was pretty bright. Down to 108. Okay, so we're up to 260. Let's give this a shot. See what happens. Wow. Okay. 332. Okay. Okay, so we're up to 280 volts, and let's give this a shot. Oh, and there we go. Wow. Very sharp transition. Let's try playing that video in slow motion and see what really happened. That was pretty fast. That was pretty loud. Wow. Okay, so if you watch the video, I'll play it a little bit slower. It looks like the whole capacitor jumps off the table, and when it comes back down, since it goes out of frame, and when it comes back down, both plates are together and they only separate once they hit the table. So the whole thing jumped off the table as a single unit. It's not like the thing was blown apart from the spark, which is very strange. Anyway, very interesting, huh? Okay, in case I didn't get that last voltage, it was 152. And it looks like that put a freaking, let's take a look here. Yeah, it looks like I put a crater into our smoothed electrode. What is that? Several millimeters, 3 or 4 millimeters in diameter. Wow. Okay. I'm not sure where the other piece went. It took off going pretty fast. Oh, there it is. It's down there. Oh, shit. It's the bottom electrode. It looks like I damaged that in the same spot. Okay. Very cool. Huh? That's weird. The top electrode is still up there and the bottom one shot off someplace. That's really bizarre. Okay, wow, that was one heck of an explosion. And if you look at the plates closely, it blew little divots in there, and it looks like a localized arc. If we can, where's our camera? I don't know. Anyway, and that on the other electrode as well, a localized arc there. Blew the copper out. Maybe it's a half a millimeter deep or more, maybe a millimeter deep. Yeah, it really blew out the copper on that thing. So if we go through the numbers and do the calculations, I'm calculating about 4.6 megavolts per meter, which is a little bit over a factor of 10 lower than the accepted value that I got. I have to maybe look back at that because sometimes dielectric breakdown is related to how much time you leave it on there, because I know some of these pulse power machines use water lines because they can store a tremendous amount of energy, because the dielectric constant of water is 80. It's huge. It's way huger than pretty much it's the largest dielectric constant I know of any material, and it has a huge dielectric strength, but only for a very short period of time. So some of these dielectric breakdowns, you know, when they put on a water line, they can hold it there for a few nanoseconds before it breaks down, and then they discharge it out so they can compress the energy in a water line in a pulse power system. So maybe these quotes are for a very short time period, like on the nanosecond scale. The longer you hold the charge on a capacitor, it's more likely it is to break down. So maybe that's it. We're holding the charge on there for until it basically breaks down. So maybe this is a lower value that we're getting, the 4.6 megavolts per meter. And there's some error on that, but it shouldn't be a factor of 10. It should be like 10% or so. So anyway, very interesting. Maybe making some progress in understanding this water arc explosion. Very cool science. This is Dr. Janes, and thanks for watching.